In this lecture, we are going to look at a notebook which demonstrates the use of a feed-forward neural network for regression. This lecture is going to walk you through a prepared Colab notebook, although a very good exercise, which I always recommend, is once you know how this is done, to try and recreate it yourself with as few references as possible. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. The important thing about this notebook is that, unlike the other examples we did, this one is going to involve synthetic data. That means data that we are going to create rather than data we've collected from an experiment or a database. Now you might ask, why should we do this? Is it even practical? Is this just a lazy programmer being a science geek? And of course, if you think any of these things, you are wrong. Using synthetic data is very important for understanding the behavior and quirks of any machine learning algorithm. You want to be able to see where it succeeds and where it fails. The important key word there is see. We'll be creating a data set which we can actually visualize and look at, so we can observe that the neural network will create a prediction surface that corresponds to the true function that we generated the data from. Of course, don't take my word for it that this is important. One great example of this is in the field of clustering. So if I go over to scikit-learn's webpage on different clustering algorithms, you can see a ton of examples of this. In particular, it shows a set of some pretty contrived two-dimensional data, and then it compares how each algorithm clusters this data. By doing this, we can see where each algorithm is successful and where it is not. In fact, this is the same thing you saw in the TensorFlow playground. Without being able to see the decision boundary and the corresponding data with your own eyes, you can imagine that this website would be much less engaging. Okay, so now you know why visualizable synthetic data is important. On to the code. As usual, we're going to start by importing PyTorch, NumPy, and Matplotlib. We'll also need this 3D thing to help us make three-dimensional plots. Next, we're going to create the dataset. We'll start by creating the inputs x, which will just be two-dimensional data points uniformly distributed between -3 and +3. As you know, the random function returns data uniformly distributed between 0 and 1. So if we multiply by 6 and subtract 3, this scales the data to be between -3 and +3. Next, we calculate the target's y, which is just the cosine of 2 times the first feature plus the cosine of 3 times the second feature. Now you might ask, why am I using this function? Is it some kind of special function? The answer is no. I just wanted a nonlinear function with a few bumps and curves, and the cosine does just that. Next, we're going to plot this data on a 3D scatter plot so that you can see what it looks like. So let's run this. Now, one thing I don't like about Notebook, compared to running a real Python script, is that you can't play around with the plots. So for stuff like this, I like to run the actual Python script on my own computer, which shows you the plot in a separate window. Then you can zoom into the plot, rotate it, and so forth. This makes it a lot easier to get a good feel for the data. Right, so if you run this on your own machine, you'll be able to rotate the plot and look at it from different angles. So you can really see what the underlying function should look like. So next we're going to build the model. Since the data is in the form n by d, where d equals 2, there's no real pre-processing to do. So this is almost the same architecture as the previous example. We have one hidden layer with 128 hidden units and a ReLU activation. The difference is now we have 2 inputs and 1 output, instead of 784 inputs and 10 outputs. And since this is regression, there's no activation function. And we're regressing on a single scalar value, so the output dimension is 1. Next, we're going to create the loss and optimizer. Since we're doing regression, we'll use the MSE loss. You'll see that instead of using the default atom, I've set the learning rate to 0.01. Now you might be wondering, where can I learn about all these different optimizer objects and what their arguments are? The answer is, as always, the PyTorch documentation. Your next question might be, how do I know that a learning rate of 0.01 is good? And remember that this is because I actually sat down and tried it. This is the only way. Again, if you're ever wondering how many epochs or what learning rate should I use, the answer is to try it and see. Next, we have our training loop, which I've put into a function. This may or may not be useful in the future for copying and pasting. In any case, I just wanted to show you an alternative way of writing this. Other than the fact that the loop is a function, nothing else here is new. Next, we're going to plot the loss per iteration to confirm that the training process converged nicely. If it doesn't, that means you have to go back and modify your hyperparameters. So this appears to look okay. Now we have the next step, which is to make predictions using the data. Since this data is two-dimensional and visualizable, we have a very nice situation. We can actually plot the entire prediction surface as a function along with the original data points. This will confirm to us that the neural network, even though it's just a bunch of linear equations with ReLUs, can approximate this sum of cosines. That's pretty amazing if you think about it. We can approximate a cosine equation without having any cosines. Now, some of you might be wondering how we actually make this 3D surface plot, so let's go through that. The first thing we need to do is create a mesh grid. We can start by choosing points along the x1 axis and the x2 axis, which I've said are just 50 evenly spaced points between -3 and +3. So that's what linspace does. Next, we call the mesh grid function, which basically does the cross product between these two sets of points. So every x1 and every x2 paired up with each other. We assign these to the variables xx and yy, which represent the first axis and the second axis respectively. Unfortunately, this data isn't in the right format for our machine learning model, which expects an n×2 array as input. In order to convert this into an n×2 array, we're going to flatten xx and yy, pass it into the vstack function, which stacks these two arrays vertically, and then transpose the result. You can do some simpler examples on smaller arrays to confirm to yourself that this does the right thing. Next, we use our model to make a prediction on xgrid, and then flatten the result, since the result is n×1. Finally, we call the plot trisurf function, which plots the 3D surface. The first three arguments are the x1 axis, the x2 axis, and then the function value, which is y hat. The other arguments are not so important, but you can play around with them if you want. So let's run this. Okay, so we can see that the neural network manages to approximate this function quite well. As mentioned previously, you get much more out of being able to manipulate the plot by rotating and zooming in. So as an exercise, you might want to try exporting this script as a Python file. So the way you do that is File, Download.py, and then run this on your local machine. So I'm going to finish running this on my machine. So here was the loss. Here's the predictions along with the original data points. So it really helps to be able to rotate it and spin it around. All right, and the last thing we're going to do here is try to test out if the neural network can extrapolate. So we know that the cosine function is going to repeat periodically from -infinity to +infinity. So you might wonder, can the neural network figure that out? So what I've done here is I've changed linspace to go from -5 to +5. So just to make it a little bigger. And if we run this, we see that it doesn't quite work. So it just assumes that the pattern keeps going in the direction it was going at the edges. And of course, this is because the neural network doesn't use a periodic activation function. So we wouldn't expect it to be periodic with respect to the inputs.